This is just
As always, here is the green folder. Please, corrected homework here. Solutions here.
yeah. I got messed up.
Oh, sorry. Homework assignment for Friday here is a lot of writing, but it's just because I'm trying to explain what I'm trying to explain, okay? And there is an assignment of homework, and that homework has to do with, well, the last topic we've been talking about is Ampere's force law. Today I'm going to talk about Ampere's circular law, but this is about the force law, and I sort of predicted. I mean, one circuit is going to be a big, long, straight circuit, which we know what the B field is for that, easy to get, I hope, and then a loop. Now there's a little twist in that, it's not just a force, but when you got a force, an engineer thinks, hey, I got a force, let's move in that force. Well, I mean, hey, let's do some work. So that's what I want to do. I want to take that loop, get some force on it as a function of distance, and then pull it away from the circuit number one. That's what I'm doing here. So it's building essentially on what you already know, I mean, energy and all that kind of stuff. But in the case of two currents flowing in the presence of one another, with forces between them, a la Mr. Ampere. And I forgot to bring Mr. Ampere's picture. Actually, it's a sketch. It isn't a photograph or anything. Ampere was an interesting cat because he really didn't make it, so to speak. Now, what do I mean by make it? Well, he wasn't. It wasn't until he was 40 years old, which is to you guys, antique. But 40 years old before he actually found a position at a university, and even then it was sort of a third-class university. Found a position that where he could feel a little secure and do his work. And it was then, when he had, a little security and a little bit of peace of mind, that he began to do his work. And of course, right at that time is when Ørsted found out, hey, there's a connection between currents and magnetic things. And then Biot-Savart, also Frenchman, came up with the Biot-Savart law. And Ampere then worked on this and wrote this magnificent 1825 paper where he explained force on another current and stuff like that. But in that paper, he also discussed lots and lots of other things which have come to be true. And maybe when I get into iron, I'll talk a little bit about that. In other words, he had the idea of, can you imagine, of atoms. The idea of atoms in the iron. And atoms are made up of little charges, zip, 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 running around on circles. By George, that's like a little loop of current. And that little loop of current, he was like, hey, I talked about there's forces on currents. If there's a B field due to a mother here, I'll bet you any money there are some forces on those little loops running around inside the iron. And that's how we analyze iron. Instead of stretching, like, in a dielectric, it's these little loops that are turning around, you'll see, lining up with the P field. That's all Ampere's idea. Amazing. I mean, it's so far ahead of his time. And here the man had trouble finding a position until he was 40 years old. People didn't realize what they had there. Well, anyway, what I want to discuss today is Ampere's second law. The first law was the force law. The second law is called the circuitous law. Totally different law, totally different. And it has something to do with this force on loops and stuff like that, but also more than that. So to start things off, I was thinking, how should I present this stuff? Not that it's new to me, but how do I present it? And I thought maybe what I might start with is actually something that we already, like I always like to do, start with something that we already know. And what we really know, I hope, what we really know is lots of electrostatic stuff. And if you recall, one of the electrostatic things that we came up with was, the electrostatic field is conservative. And of course, there are nice ways to write that, but the most subtle way was that, the curl of that electrostatic field was equal to 0. If it was equal to 0, in other words, if I put a paddle wheel in that field, it didn't turn no matter how, anywhere, or any way I oriented that paddle wheel, it didn't turn. And therefore, the curl was equal to 0. That's the kind of thing. And it's the nature of the field to be conservative. All right? And then, laminar, the geometry would be laminar, and then the mathematicians, it's curl-free. But that's a very subtle way of saying it's conservative, which is the physics-y way. In other words, if I start at A, and I take a path around here holding up a coulomb of charge and go back to A, I will have done no work. That's the physics-y way. That's the way we like to think about it, okay? Now, I haven't discussed it. I should have probably when we first started magnetostatics. But over here, like I have a permanent magnet, North Pole, South Pole. I remember I told you, I should use color maybe, I told you, hey, there's something different. And they recognized this, the old boys knew this, that, have these, what we now call the B field, starting out in the North Pole and winding up at the South Pole. Well, it's just like, in the electrostatic world, I have a positive charge and a negative charge. And, the lines of E went from the positive charge to the negative charge. In here, I got these North Pole, South Poles, or magnetic charge, or whatever you want to call them. But the B field, we don't describe it with E, but that B that we describe is given as going from the North Pole to the South Pole. The only thing is that sneakily, that thing goes straight through and it turns back on itself. It's like that dragon eating on its own tail. Every time you try it, you get these lines that are continuous. So the geometry, that's a solenoidal field, see? And so then, if you recall, I'll go back here, the second thing that we found out, and I'm going to go through the steps to get to this point, but I'll tell you the end point because it's going to be important to us to follow the same steps in the magnetic world. We followed from Gauss's law, we followed a chain of reasoning that said eventually that the divergence of, let's say epsilon 0 E, and sometimes we call that D, was equal to rho volume, the charge density. This was how the field, that field, is connected to the mother source. Remember that? Those are the two defining equations of electrostatics. How, if this is the mother, this is the start of it all, tensing up the universe, and if you take a little box and you ask how much of this stuff is going out of the box minus how much is going into the box divided by the volume, as you squash down to a point, that's what this is. It says, that's equal to the charge at that point. If it's positive, if more is going out than coming in, well, then it's positive charge. If the opposite, then it's negative charge. You can have them both. So it's a charge finder, right? The divergence, the little box, is a charge finder, and the paddle wheel is a describer of the character of its conservative field. That's what this says. And those two equations essentially are those of electrostatics. And if you were a philosophical kind of guy, that's where you'd end it. But of course, we're engineers, so we have to use those equations to come up with solutions to fancy-dancy problems and stuff like that. But this is it for electrostatics. Statics, later on, this is going to be a problem. But right now, when the field is steady, no problem. Well, now the reason I introduced this is you might say, oh, I know how to find where the currents are that cause that magnetic field. And don't forget, as I told you, gosh, you don't have to use a permanent magnet. You could use a little coil like this, a solenoid, and it causes a magnetic field just like that. I mean, it looks like an imitation. This is an kind of electromagnet, and this is a permanent magnet. But the same sort of field due to both of them, right? And so what you would say is, well, if it was good enough for the electrostatic world, the divergence, the little box idea, should be good enough for the magnetic world. Where are the north poles and south poles? So you should use color again. Make a little box, roam around the universe, put the little box here. How much B field goes out, how much goes in? Same out as same in. No, there's no current here. How about over here? No, there's no current here. So you come around here and you put the little box here, or you put the little box here, and you measure how much is going out minus how much is going in, and it always, even though you're right on top of the damn source, it always turns out the same amount of B is going out as is going in. The box is the wrong tool to use to figure out where the hell the current is or where the North Pole and South Pole are. It's like using a hammer where you're supposed to be using a screwdriver. It's the wrong tool for the job, all right? So the divergence is not the right thing. So what we have to do is say, oh, well, then what kind of device would I use in order to discover where either the current is that's causing the field or the North Pole, South Pole complex, the permanent magnet, where are they causing the B field to tense up the universe everywhere, all right? That's our task. And that's what Ampere's circuital law will do for us. It will give us the connection between the field and the source. Only in this case, the source is a current. In this case, of course, the source is a charge. Now, the way we describe this is, I mean, if you got a divergence, and the divergence is always zero, I guess the way you'd write it is well, maybe I should write it on top, because that's where we start. The divergence of B is equal to zero. As much always, I don't care if you're laying on top or you're laying a mile away, doesn't matter. You aren't using the right tool, and basically you aren't discovering where the current is. So this is the divergence of B is equal to zero. And it's not only zero, but it's always equal to zero. Even when the B is going to turn into a script B, time varying, it's going to be equal to zero. And just like over here, the physicists, us engineers, say, oh, that means it's conservative. And I know what that means. What does this mean? Physically, what does this mean? What it means is that you will never find just a North Pole sitting all by itself. There's always connected to it a South Pole. If there was as they say, a magnetic monopole, one pole, just like you could have one charge. If you had one of those, well, then you could put a box around it, and then you'd find some B was going out, some B going in maybe, but the out would exceed the divergence wouldn't be equal to zero. That can't be, because you always have a North Pole connected to a South Pole. So really, what this is saying, the way to say it is no magnetic monopoles. That's the physics guy's way of saying it, just like the physics guy is saying conservative over here, that equation. So it's a subtle way. Now you guys are getting pretty subtle. I mean, you know what divergences are, you know what, and you know, it's kind of like a little box. You know what a curl is, it's like a little pad wheel and all that stuff. And so the fraternity of electrical engineers understands what this means and what that means, okay? A very subtle way of describing pretty simple ideas, actually. Physics, simple ideas. So the task now is, well, my task is to go through and show you, well, the analog of this thing. How is the B field, not the E, but the B field connected, well, not to charge, but charge moving called current? How is that? How is that done? And that's going to be Ampere's circular law. Now to do that, I thought I might make a parallelism. I mean, the steps in that argument going from Gauss's law, I'll start with Gauss's law, to this point, is exactly parallel to starting out with a law and getting to the point that I want to get. I won't tell you the secret of life down here at the end, but step by step by step by step, they are parallel to one another. Well, what are the steps? Well, if you recall what we did, I'm not going to lecture in detail, but if you recall what we did is we took a point source, a Q, and we surrounded it with a surface, a sphere. Do you remember? A perfect sphere. And then we came up with the idea that if you do the integral all the way around this S of epsilon 0 E dot ds, and sometimes you call that D, you know, understand that stuff, coulombs per meter squared. It was equal to the Q enclosed. Enclosed, right? And then what I did is I said, well, that's an awfully special surface. So what I did is I said, okay, let's take that Q and surround it by, you know, some general surface like that, but surrounded like that. Again, it's a surface. Don't forget, we're talking about 3 dimensions here, surrounding some sort of a volume, let's say V sub S or something like that. And then what I did, if you recall, the way I did it was I made an approximation. Arc, radius, arc, radius, arc, radius. I made a lumpy kind of approximation of this whole thing. And all the arcs added up and all the radii didn't, because essentially when I did this integral on the radii, this dot product did away with that part of the integral. So I wound up, and again, all the details, I wound up with any here. In other words, oh, you don't have to have a sphere. You can have some weird bubble shape like that, right? So you could add that to it, if you please. And then what I did, the next step in the logic was, what if I have, you know, like a Q and the bubble is over here? And then what I found out was that integral was equal to 0. And then I'm beginning to get the idea that it's this, and I shouldn't have probably written this yet, but it is the Q enclosed. If there's nothing enclosed, then that right-hand side is equal to 0. So this, and then elaborating it here and elaborating it even more here, I came up with any kind of a surface you want to, is equal to, of this epsilon 0 E dot ds, is equal to Q enclosed, right? If it's not enclosing it, if there's no Q in there, it's 0, right? And then came the thing, well, why this point source Q? We all know they can't get a point source, so let's hammer it out and make sort of a cloud or something. So this is the rho volumetric, you know, coulombs per meter cubed, and then surrounded. And by superposition, I didn't argue that too strongly, but by superposition, I can say basically, whether you got it all lumped up at one point or you got it sort of spread out, this same thing holds, all right? And then the last thing is to say, hey, I haven't got room down here, here is that cloud, rho volumetric, and here is the surface. It's If it was equal, it was way off to the right, well, then that would be equal to 0. It doesn't enclose any charge. Cloud or not cloud, doesn't matter. But let's say it's going through the damn cloud, then you find out it is only that part that is enclosed by that surface right there, right? So we wind up with essentially the integral over any surface, and now that includes enclosing the whole thing, not enclosing anything, enclosing half of it or 1/10 of it or whatever. Any SC of epsilon 0 E dot ds is equal to the Q enclosed. And that could be written as the integral of the rho volumetric d volume over the volume that is surrounded by S. So this is the volume surrounded by S, but only this part contributes, because that's everything else. When you do this integral, what is the rho over here? 0. What's the rho over here? 0. So actually this accumulates value only when you're talking about this region right here. And remember, that was the absolutely amazing thing about Gauss's law. I mean, this whole cloud causes an E field on the whole surface everywhere. And yet when you do the integral over that surface, only this part of the charge is really effective in that integral, right? The right-hand side. You understand? That's what makes that. It's an unbelievable theorem. That was Mr. Gauss at work, a first-class mathematician. Thinking that way. And then the next step, remember the last step was, oh, well, if you can take a volume like, like that, why not take a smaller and smaller and smaller volume surrounded by a smaller and smaller surface? Do you remember that? So what we did there is we said, well, I have, this is Gauss's law in integral form. I mean, this is the way I wrote it. And then, but a surface integral, a double is equal to a triple. So if I could just make this surface integral into a volume integral, then maybe I could equate this integral to that integral and take advantage, and there should be an any here too. Any, if you recall, that any is a very important thing. And that is essentially, if you recall, the divergence theorem. In other words, an integral over of any kind of a vector, you could call it A. Now our A is epsilon 0 E dot ds is equal to the integral of the divergence of epsilon 0 E d volume. And it's an identity. Sine squared plus cosine squared is always equal to 1, right? So why would you write sine squared plus cosine squared? Just sum the two up and get a 1 there. So that's really an identity. So what I'm saying is, hey, I can substitute for this surface integral, I can substitute a volume integral. I can put it right over here. And now I have a volume integral equal to a volume integral. Now just because two integrals are the same doesn't mean that the integrands are the same. I mean, just because, the integral of this one, the area underneath there is equal to the integral of this one doesn't mean that this function is equal to that function. No, I mean, the integrals are the same, but the integrands aren't. I mean, the thing you're integrating doesn't have to be the same. The area is the same. But if you try that integral over this range, this range, this range, and they always turn out to be, the integrals turn out to be the same, then, and that's what I have here, that's why that any is important, then you can say, oh, this guy is equal to this guy. In other words, you have the divergence of epsilon 0 E, the divergence of epsilon 0 E is equal to rho volume. And that was what essentially I had here. Right? That's how I got to it. I started out with Gauss's law. I went through a logic to make it generalized, kind of as general as I could get it, this being the most general, and then I squished down around a point. I used this wonderful divergence theorem, which is math, and I wound up with this differential form, point form of Gauss's law. Remember that? That's how it was. And then that's when we came with the idea, oh, a little box is what you discover where the charge is. That was the whole reasoning that I followed through. I spent damn 15 minutes doing that. Now that's not a lecture, that's just kind of guiding you here. Now, let's do the same thing in magnetics, right? And what do you do, how do you start there? Well, like here you had a charge. What do you think might be the analogy of a charge? Well, take the simplest current you can think of, an infinitely long wire of current. That's the kind in your homework for C1. Just a hair of current flowing up the z-axis. So again, I will picture it as coming out toward you. I won't picture it like this. I'll picture it like this. So let's say it's coming out toward you, and that's the B field. Excuse me, that's, what am I saying? That's the current, right? So you have so many amperes flowing toward you in the room on an infinitely long, and then you know what the B field is like at a distance rho. The B field looks like it's, well, again, if I'm in the cylindrical coordinate system, this is direction phi, so it's in the phi hat direction, always running around like that, and it's proportional to the current, sure, all over 2 pi mu 0 inverse rho. It goes as 1 over the distance away, and that's the one you're going to use in your homework to find out what is the B field near the little C2 loop, right? That's what it is. It gets smaller and smaller as 1 over the distance away from the mother source C1. Okay, now this step here is comparable to this one here, where I've used, in this case, three-dimensional sphere, surface business. Here, what I'm going to do is say, well, I mean, let's play. I suppose this is what Ampere did. Just like Gauss did. He said, well, we got the E field, and it goes down as 1 over r squared. Let's do an integral around a ball around it, right? That's how we came up with Gauss's law in integral form. Well, here, the step is, well, it's not you can't enclose an infinitely long current. You surround it, right? You encircle it or something like that. So I suppose what you could do is say, take an integral all the way around, some sort of a contour of B dot dl, where the dl is this, like this. And that, of course, is rho d phi. So this guy is in the rho hat direction, and it's rho d phi. You understand what I'm saying? I mean, that makes sense. And then you stick this guy in here, you say, oh, phi dotted into phi, hey, that's 1. So you get rid of that. And then I, well, that's a constant. 2 pi is a constant. Mu 0, all that business. And then you do an integral on phi going from, well, all the way around. So 0 to 2 pi of d phi. And out here you had an I and a 2 pi and a mu 0 inverse. And then down here was a rho, but down here was a rho, but up there was a rho too. So that canceled out. Okay? Got that? And then this is just equal to 2 pi. And so the 2 pi cancels the 2 pi. So that integral, B dot dl, is equal to the current divided by mu 0 inverse. And just like, that's what happened there. And then remember, it was sort of like the integral of E dot ds was like the Q enclosed divided by epsilon 0. So I just brought it over here. Well, that's what I'm going to do here too. I'm just going to say, well, hell, if that's that, then I'm just going to put the mu 0 inverse here, and I'll say, oh, mu 0 inverse B dot dl is just equal to, by George, the current, well, not enclosed, but encircled. Okay? I mean, that makes, use that word, not enclosed. You don't enclose something infinite. You encircle it. You walk around it. Question?
So you said you were going to picture it coming out to us, right?
Speak loud because my ears are lousy.
You said it was going to come out, right?
The current.
Yes.
No, the circle is in the plane of the board.
Yes. So would it change if the current was like the opposite? Like instead
Then the
of
B
going-
would change.
Yeah.
It would reverse also. And yes, yeah.
Okay.
And so you would still go around that, but you would get a negative sign because now the current you say is going in instead of out. But the B has changed, but the DL is still rolling around. So the dot would give you a minus sign. Yeah. Okay. Which would mean that it's in your coordinate frame, it would be going in. Okay, so this step right here, this thing right here, is comparable to the first step here. So then the next step, what was it here? Oh, let's not consider a circle. That's too special. Let's consider any old kind of a contour. So that's the case where I have, let's say, the eye coming out to you, and this is the C, the encircling. And then you use the same argument. You make an approximation, you know, an arc and a radius, an arc and a radius, an arc and a radius. And all the arcs, because the integral here, because this is dependent on rho and this is 1 over rho, independent of rho, all the integrals over the arcs are going to be the integral you're looking for. And all the integrals over the radii are 0 because essentially your DL is in this direction, but your B is in a perpendicular direction. And you know, the dot product between two perpendicular things, orthogonal, is 0. So basically, this, using that same argument as I really did here, except they weren't just arcs, they were like little surfaces and another little surface, approximate little surfaces with radiuses connecting them. This is three-dimensional, and this is in some sense easier, it's two-dimensional. The same thought process leads us to the idea, oh, the integral of mu 0 inverse B dot dl, all around that contour, is equal to the current encircled. And now you can say, oh, that's for any kind of a C, right? Like that, I mean, any shape. And then comes the next question, as we had over here. Oh, what if your damn contour, this is of course a surface here, but a blob, like a balloon or something. But now I'm thinking in terms of contours, then what if I had the current here and the contour was out here? Well, it turns out that that is equal to, I mean, if you take a look at that one, it turns out that that's equal to 0. So that fact says, oh, that's the current encircled. Like that. So we're getting more and more narrow. I mean, well, narrow or maybe more broad. Any contour will do on this thing, not is equal to the current that is encircled. And here, it ain't encircled at all, so it's equal to 0. Now the next step was, oh, hey, let's not have a very hair wire coming out here. Let's have a fat wire. So I have, in this case, let's say current flowing all through this copper rod here, and not on a little fine hair, but all over this place. So let's say out, 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 out. It's a big, thick wire, so to speak. Now the way to describe it, the whole thing is maybe so many amperes, but the way to describe that is J volumetric, right? In other words, amperes per meter squared. The volumetric current density, amperes per meter squared. You know, per meter squared, that's how many amperes here, per meter squared here. And you would integrate over the whole damn thing, you'd integrate this J, amperes per meter squared, times the integral, you know, D surface, and you would get amperes out of that baby, right? That's coming out at you. And then you surround that, and by George, you would get, I mean, by, again, superposition, you would get exactly the same result. In other words, whatever is encircled, mu 0 inverse B dot D over this contour would be equal to the I encircled. And then comes the final blow, and that is, well, what if the current is flowing on this heavy-duty wire here, like this, where I describe it with J volumetric, but my contour is this. Then only the current that's flowing in that region counts. And that means that it, again, is only the current that is encircled, and then you can write this as integral of J volumetric dot ds, and this is the S surrounded by C. So you would integrate over this. This is C, this is S sub C, but again, how much J is flowing here? None. None. So most of this is not gonna contribute at all. But when you hit over here, by George, then this is gonna be not zero and you will be start contributing. If you're over here, basically, that will cause a B field around this guy, right here, but it will not contribute to this integral. Same thing as we had in this wonderful, wherever I wrote it here, this point right here, right? So that's what I meant when I said I'm trying to develop Ampere's circular law in exactly the same sort of steps, getting more and more complicated. I mean, as I go through from a circle to any shape to a stretched out kind of a current to encircling only part of the current and stuff like that. And then the next step is, well, what was the next step here? Oh, the next step here was, make that surface real small, make that volume real small, and come up with this, okay? Remember that? That was the last step, and then we call that Gauss's law in point form, where we started out in Gauss's law in integral form. This really, so this is the integral form, this is the point form. And this right here is Ampere's circular law in integral form. That is the comparable thing to Gauss's law in integral form. And the next step is to make these volumes and these surfaces small, or in this particular case, to make this surface and that contour surrounding the surface very small. We're going to crunch down around the point. Now again, just like before, we have, we got a damn line integral equal to a surface integral. Well, here's where what you do is you use, well, not the divergence theorem, like I used there, but you use Stokes' theorem. Now you have to go back to where I discussed the curl to read about the Stokes' theorem. But the Stokes' theorem says, I'll try and erase this. The Stokes' theorem says, if you have an integral around, let's say this could be an A, any kind of a vector, but our vector is this one, so might as well use it right now. Inverse B dot DL over any kind of a contour you please. It is always equal to, again, it's an identity. Sine squared plus cosine squared is equal to 1 every damn time you try it, any phi you want. So it's an identity, and it's equal to the integral of the curl of whatever this was. That's mu0 inverse B dot ds over the S that is surrounded by C. This is Stokes' theorem. It's just math. I mean, it's don't think of it as anything deep and philosophical. It's just like you really think philosophically about sine squared plus cosine squared is 1. No, you just use it. Come on, you use it. So that's kind of like this. It's a tool. Pull it out of your toolbox and let's use it. Right? So that what that says is, hey, for that guy, I can substitute this guy. Okay, then I have a surface integral equal to a surface integral. That's nice. It still isn't enough because, as I told you, two integrals can be equal to one another, but that doesn't mean the integrands are equal. But it's this any that saves us. Just like that's the any in these kind of integrals, where if it's the same, no matter what range you're on the integral, they always turn out to be the same on both sides of the equation. Well, then the integrand is equal to the integrand. And that's the same thing here. Well, that means that this thing, the integrand, is equal to that thing, the integrand. And we wind up with the curl of mu0 inverse B is equal to J volumetric. What does that say? I mean, that's the math. But what is a curl? Oh, that's a little paddle wheel. So what you do is you got this B field out here due to mother. Got the B field, tensing of, you put your paddle wheel in. It's not an electric field anymore. You did that a long time ago. You put that paddle wheel in there and you ask, is it turning? No, it's not turning. Well, change the direction. Oh, it's beginning to turn now. No, it's going faster now. No, it's 0 again. what you do is you turn it around at the point of interest, and you see where is it spinning the fastest, and you look at the right-hand screw rule, and it gives it a direction. This is a vector quantity. It has to be a vector quantity, just like this has to be a scalar quantity because that guy is a scalar. This has to be a vector dude on the left because that's a vector. The current is pointing after all. What direction is it pointing in? Well, it has something to do with the direction of the curl. Understand that? The direction of the axis around which this paddle wheel is spinning. And then the side, the rate of spin is proportional to the size of the current. And so what you do is you wander around with your little paddle wheel, and it ain't, no matter how you twist it, it ain't turning. Oh, there's no current there. Not here either, not here either. And then suddenly, oh, hey, it's beginning to turn. Let's twist this baby around and see where it turns the fastest, and that is going to, the right-hand screw rule, is going to give you the direction of the current, and the fastness is going to give you proportional to the size of the current right there at that point. Got it? So this is a current discoverer, where just like this is a charge discoverer. So it's just the opposite. The divergence operator tells you where the charge is in the electrostatic world, and the curl guy tells you what the source of the B field is, the current in the universe. So we wind up with, just like, I surrounded it over, just with two equations. I mean, the conservative nature described by the curl of E always equal to 0, and then this is the charge discoverer here, the little box idea. Here in this world, we come up with, the describer of the field is the divergence of the B is always equal to 0. That's the nature of the field. It is divergence free. Just like that guy is curl free. This guy is divergence free. And now the second equation is, by the way, the curl of mu 0 inverse B is equal to J volumetric. So this is comparable to what I drew on the extreme left. This is a property of the field, just like that's a property of the field. And the bottom equation is how you connect the field to its mother source. This is how you connect the field to its mother source, which is a current. Okay? And these are the two equations of magnetostatics. There ain't no more. This is it. Those two equations. I mean, and now, if you really appreciate what I've done here through this course, and 311 too, I mean, this is, and you understand the mathematics, these symbols and stuff like that, you're a pretty powerful person. You really understand what's going on here. And now what we're going to do is we're going to use these equations intelligently and those equations intelligently and come up with very useful results. But the point is, this is magnetostatics, and it is statics, and this is electrostatics. And that last equation is Ampere's circuital law. Now, I have to say, and I say this in the homework assignment, that Ampere's force law, he has two wonderful laws, this one and the force law. I crossed into the B of a mother source and all that stuff. That force law is more what you'd call practical. That's how motors are rotated. You know, that's what motivates a motor to spin. Ampere's force law. This, if you think about it, well, it's sort of academic in a way. I mean, yeah, it gave us the connection between the source of a B field and the B field itself. Yeah, okay. So in that sense, this is more philosophical than the force law. The force law, you study that in motors, they'll describe it as BIL. That's the way they'll say, BIL. The I is the current, the B is the field, and the L is the length of the coil in the field. the armature of the motor or something like that. And that's going to be the force that's going to spin the motor around. And it goes further than that. If you take a motor is kind of like a round thing, right, with an axis and it's spinning. But if you take that guy and slice him and open up that baby, you have what they call a linear motor. And then you don't just make it that long, you make it real long, like from here to Cincinnati. And then what you do is you put on that motor, the stator of the motor, you put a thing called, a railroad car. And then you excite things just right, that railroad car will lift off, and then just like the thing can spin around a rotating one, that car can be motivated to move along this track. That's a magnetically levitated train. Okay? All that stuff comes from Ampere's force law. Both the lifting of the train off the tracks and the motivation of it to push it down the train. And that's not academic. The Chinese, of course, they got a lot of money. The Chinese have already a 26-kilometer magnetically levitated train that goes about 300 miles an hour going from Shanghai downtown to their airport. And they plan to build another one much longer to Beijing. So, I mean, it's working, obviously, it works. It's Ampere's force law. That's an important law. Now this, like I say, but you might say, oh, well, what use is this? Well, when we start getting into propagation, when we start getting radio waves going through nothing, that's when this becomes important. So when we get into antenna kind of stuff, where we're out in free space, and electromagnetic waves, and wireless, and why the hell am I getting this signal in this little phone that I got to my ear, that's when this comes important, okay? Again, not academic, but right at this point, it's a little like, so this is electrostatics, magnetostatics. Now, just to give you a hint of where this is going now. Now, we're not at the end of this story. Where this is going is this guy right here ain't right when this is time changing. And when this is time changing, I'm going to use a symbol del cross that. And I could write it like this, but you don't even have to do that, because when I write script, it means, oh, that's time varying. Then that is not equal to 0. This one stays fixed. Wonderful. I don't care if this is time varying or not, that's going to stay fixed. So this can be a function of time. I mean, the charge is moving and bouncing around and changing with time, big and small and all that stuff. This is changing, therefore, but it stays the same equation. Same thing over here. If I take this equation, I don't care if you're in a dynamic world or a static world. There ain't no magnetic monopole. There just ain't no magnetic monopole. So this is going to stay, even if this is B as a function of time. I mean, nothing new there. I'm talking now about the second half of this course. We're getting into the second half of the course, the dynamics business. But this one is wrong. Well, it's not wrong. It's okay if you're at statics. But Mr. Maxwell, which I'm going to talk about Mr. Maxwell, he's not the dog, but the man. Well, put it this way. This one, he didn't write it this way, but I'm going to talk about Mr. Faraday too. Mr. Faraday said this isn't right, and he told us what this has to be, not 0. What is it equal to? That's going to be Faraday's law. Extremely important. How do antennas work? This is explained by that. This is going to stay the same. So this will change a la Mr. Faraday. And then Mr. Maxwell said, I believe Faraday. That's a whole story in its own right, because Mr. Faraday went to the 6th grade, but he was a genius. And all the mathematicians, all the other physicists around Europe said, that's bullshit. I mean, he can't be right. He's 6th grader, and I got a PhD. And so nobody believed him, except Maxwell. And of course, Maxwell was way heads above every other physicist that lived. So basically, he said, I believe in this field concept that Mr. Maxwell came up with, Mr. Faraday came up with, and I am going to mathematize this stuff. I mean, so he accepted not the 0 here, but what Faraday put here, and he accepted this, and he accepted no magnetic monopoles. He accepted that. That's basically belief. I mean, there are no, we've never discovered a magnetic monopole, so we're just believing that there isn't one. And then he looked carefully at this, and then he found something is not right. And he had to add, I won't tell you what it is, another term here, and that corrected it. And this was Maxwell's contribution, really. I mean, Faraday had done a lot of work there, which he believed. Gauss had done a lot of work there. Ampere had already come to this point. A magnetic monopole, they never saw one, so they didn't believe they existed. But this one here, he played around with. And when he added this term, the real question in his mind was, how the hell does a capacitor work? I mean, you got a current flowing, you got a couple plates here, and here comes a current, open circuit, and there's more current flowing down on the other side. What happens? How can that be? How can you have current coming in and current coming out and nothing in between? No current flowing in between. It's an open circuit. How the hell does that work? That's what perplexed Maxwell. And he had to add a term here that explained that, and he felt much better. Probably could sleep at night then when he added that term. And that is probably a Nobel Prize right there. Didn't have Nobel Prizes then. And then, I mean, he didn't stop. You can't stop a genius. Then, when he had this equation, that equation, that equation, and that equation, he played with them. And he found out, hey, if you put them together, you'll wind up with the famous, guess what, wave equation. It has two solutions. And the waves, if I know what mu zero is, and I know what epsilon zero is, we know what this is, the capacitance per unit length of empty space. This is going to be the inductance per unit space. If you have those two, then you find, by George, that the speed of the wave is the speed of light. And he said that. And that was another Nobel Prize, I would have to say. I mean, so he connected electric to magnetic to light. Those were considered to be three separate phenomena in physics, and he tied them all together in one fell swoop like that. That was around, he wasn't very old. That was around, he started he was born in 1831. He did his work when he was in his 20s, started at Cambridge. I'll talk about that a little bit. And by the time he was about 40 years old, less than 40 actually, he had done all this stuff. Of course, in the meantime, he was doing a lot of other stuff with gases, and there are Maxwellian distributions and all kind of fancy things in that mag. So he wasn't, just working on electromagnetics. He's working on other things too, very important things. But he's famous for these equations that he came up with. This equation that he came up with, and then the fact that he discovered that, well, these radio waves, as we would call them, they go at the speed of light. So light is an electromagnetic wave. He came up with that conclusion. So I would say he is at least a double Nobel Prize winner type guy, which makes sense, because he's considered to be one of the three greatest physicists who ever lived. There was Newton, of course, and then there's Einstein that we know about, and then Mr. Maxwell. Right? That's why I named my dog after Maxwell. He's brilliant, too. Let's see, it's about time to shut down, I guess. I have a question here.
Oh, I was wondering if it's still the case that we don't have a proof for the non-existence of magnetic monopoles. Do we still?
No, they made an experiment, and they thought they caught one. That was maybe 20 years ago. They thought there was one, but they figured, and it may have been. They're looking for it for 20 years. They finally found maybe one, but if there's only one in 20 years, it's damn close to being none.
Sure.
You know what I'm saying?
Okay.
So that still holds. Okay, we will speak up on Friday. But we will not be in this room. We will be
Arkansas Parkland.
Yeah, no.
Sparkland.